Okay, so it seems like we are ready to go. So welcome everyone. It's definitely a new format for us, so hopefully it will be beneficial. I don't really have a response like we usually have while in front of the audience. So if you have any questions, please type it in the chat. We have a couple of people from our team to help with any problems. Also, if you have any problems hearing or maybe something doesn't appear on your screen, please let me know right away so we can fix it. So if you can't connect to Teach Cluster also, don't be shy, just make a note of that and we will help you as well. So if there are no questions right now and everybody can hear me, let's start. So today we are going to talk about creating parallel programs. So all of us nowadays have powerful computers with multiple processors in it. But unfortunately, without knowing how to access this power is kind of dormant and you only get a performance per one core. So we definitely would like to take advantage of it in our scientific computing. And OpenMP does exactly that. It's a very simple way to make your program parallel. But first, let's talk about multiple processors and in general, what are threads, workers, and so on. So your computer, your laptop, or whatever you're working on, well, I would say nowadays definitely has multiple cores. It used to be just a single core. Now it's multiple processors. My laptop has, I think, 2 processors. Your laptop might have 4, 8 if you have a powerful one. On Niagara, we have 40 processors. So you definitely would like to take advantage of this resource available to you. But you have to be aware that there is a difference between running something concurrent and parallel. So each processor you can think of as a different worker available to you. And if your workers rely on each other, meaning that the second worker cannot start until the first worker finishes its work, then you don't really get this speed up that you think you can obtain. So look at the first figure, for example. My second worker depends on my first worker to finish first, and then the second worker can start. Then the first worker has to wait again for the second worker to finish, and only then it can continue. So being concurrent, the execution is not really parallel. Another example that you can think is when you're printing something. So for example, you're sending your document to the printer, and the second worker, printer being, picking up the task, and meanwhile printing, you don't want to wait for the printing to finish in order to continue with your regular workflow. But if you have only a single processor available to you, one task, then it means, and it used to be like that a long time ago, while the printing is happening, you can't really do anything with your computer. You have to wait. Nowadays, of course, everything is done in parallel, and there are many workers or threads that are constantly saving your workflow. Maybe if you work in like a Microsoft Word or something, multiple checks are happening in the background. You're not even aware of that. So things are happening in concurrently and possibly in parallel. So we're really interested in parallel execution because if you compare figure 1 and figure 2, despite having the same workload, the second execution is truly parallel and it definitely finishes much faster. The condition here, of course, that these tasks that each worker performs are sort of independent. So they're not waiting for one another to finish. So another thing we need to talk about is the architecture of the modern computer, the modern chip. So you have multiple processors available to you. And of course, you have a common area. This is a shared memory that every processor can access, can read and write to. And that's where you store in your values, your variables, and your arrays, and so on. Now, we all know that the disk writing on the hard drive is the slowest operation you can imagine. That's well known, and hard drives are really slow. Processors, on the contrary, are very fast. So basically, you can have a very fast processor, but if you are down to writing on a hard drive a lot, you basically lose this advantage of a fast processor. Well, memory, the shared memory or RAM, random access memory, is definitely much faster than a hard drive. However, it's still significantly slower than a processor. And people came up with this idea is that let us create another layer, or it's called a cache layer, that is very close to a processor. And the speed that the data can move between the processor and the cache is very fast. So proximity on the chip matters. If something is relatively far, it means it has higher latency. So it takes longer to access this particular element. If something is very close to the processor, it's significantly faster to access the data there. And cache literally is very close to each processor. Each processor has its own cache. And the speed between cache and memory is significantly slower. So you have these three layers. You have processors, you have cache layer, and you have memory. And the cache layer could be a culprit, or it could be a very good benefit to your programming. If you take advantage of a cache layer in a smart way, you'll get a significantly boost in your performance. But if for some reason you create a code that, for example, creates a lot of bouncing between the cache lines, that will actually slow down your code without you even knowing that. And we're going to talk about this particular case that you have to be aware of. So these are basic, well, kind of architecture that's available. And originally, the idea of this multiprocessor system was arranged as a symmetric multiprocessor. So it's a theory that every processor has the same time access to the memory, that the operating system treats every processor equally. So basically, everybody is equal and there is no priority. But as you can imagine, the geometry of the chip implies that certain elements are closer to the memory. There's a certain proximity. And of course, certain processors are treated more as faster processors than others, simply because they're closer to the memory. And that leads us to a non-uniform memory access concept, where indeed the shared space memory access time depends on where the processor is located. So keep it in mind, we are not going really bother thinking of which processor is closer to the memory right now, but you need to be aware that not every processor is equal, which might change the order of your execution. Okay, so that was about architecture, and now we can shift to OpenMP. So OpenMP is an interface that has certain compiler directive and library routines that help you to parallelize your code very fast. In fact, here I have an example of one line that makes your code parallel. That's it. So everything after this line would be executed in parallel. So OpenMP allows you to parallelize your code in a very simple fashion. You don't have to take care of particular threads, and it could be easily turned off and on as well. So it's available for C, C++, and Fortran. I think maybe Ramses is an expert in Fortran, so if you have questions regarding Fortran, just type it in in your chat window, and we'll help you. But if you are not familiar with C or not familiar for Fortran, don't worry. The examples I'm going to use today are very, very simple. So you just need to know what a for loop basically is and maybe an if statement. And that's all it is. I'm using very simple examples to get you started. So Python, no. So with Python, you have another types of parallelization, and Python had its own problems with the lock. But what people do is that they create an interface. They will write a library in C, and then they will call this code from Python. That's basically how NumPy is doing that. You're using high-level functions that are written in Python, but once you run the code, actually underneath it's running C code. So that's the way you can get the parallelization. Pretty much in any language, you would need to interface it with C, C++. So yes, like C or C++ wrappers, exactly. Okay, so now let's make sure that everyone has access to OpenMP. So if you're on a Windows computer, well, my condolences. The best probably bet right now is just to connect to a Teach cluster. You probably already know how to connect there, but nevertheless, I have slides, a slide here on how to help you to do that. Remember that once you log in into a supercomputer, you don't really have anything accessible to you. You need to load the software, the modules. So in order to run GCC, you would need module load GCC. That's the command you need to type to make sure that GCC is available to you. We have multiple compilers available on the systems. So obviously, you don't want to interfere with one another. That's why we ask you to manually load the software that you really need. So you still can do this, of course, on your particular computer. If you run in Linux, I just assume you know what you're doing, and GCC should be available there. GCC is the C compiler that I'm going to use today. If you're on a Mac, that's the way I access OpenMP on my Mac. So Apple computers come with GCC pre-installed, but it's a rather old version. And the best bet is to use, for example, a package manager like Homebrew. And then I can just install GCC. So I basically have two GCCs installed on my computer. One as a Homebrew, one comes with the laptop. And in order to not confuse between them, GCC-9 is a command to access the newly installed GCC compiler through Homebrew. So that's how I do that. If I type just GCC, I still get the Apple compiler, which somehow does not include OpenMP. For some reason, Apple has an issue with that. So I prefer to use GNU compiler GCC. By the way, I didn't mention, but you guys need to take an attendance, I believe, and you need to pass the test. Hopefully everybody can do that. I believe the number supposed to be 8. So yeah, it's in the chat. So please make sure you guys pass the test. I know it's a difficult one, but please, maybe even have 2 tries, attempts, I do not know. Please make sure that the answer is 8. It's in the chat. If you have any trouble, just let us know. If you fail the test, let us know. We'll fix it. Just write something in the chat so we know you're here. Okay, so back to our OpenMP. So you've noticed probably that the way you activate OpenMP is by using a flag. So -f OpenMP activates OpenMP, and you should be able to access the full power of this wonderful technology. Okay, so somebody needs some help with the test. I think it should be resolved pretty much soon. Okay. I think you have to go to the website and go to live and chat or a test. There's a link called tests, and then you need to go and then you need to go and pass the test. Okay, you do get 2 attempts, so that's good. Okay, so let's see. So if GCC 9 is not found in the path, you need to install it. So Mehdi, do you have Homebrew installed? Yes, so as the slide says, it's ONSX. OSX refers to a Mac system. So if you don't have Homebrew installed, you can go to this link, brew.sh, and just, it's a simple command. You just copy and paste it in your terminal. It should give it to you, but I wouldn't recommend doing this right now if you don't have Homebrew installed because you're not familiar with it. So I would suggest you just go to our Teach cluster and just do it from there, okay? Then you don't need to type GCC-9, it's just simply GCC. So we do have a recent GCC version 9 installed, but the commands we're going to use today will work with pretty much any compiler, with even a very old one. Okay, so again, if you have any problems, just let us know, we'll figure it out. So by default, again, when you log into any supercomputer, you pretty much get nothing. It's all there, but you don't get it. You have to activate it. Because we have, for example, Intel compiler, we have GNU compiler, and in order to make sure that everybody gets what they need, you have to load the module. Okay. Yes, so you get an error, fatal error, no error input files. That's good. If you get an error, it means the system communicating with you because you need to specify the file to compile it. Okay, so if you get a command not found error, then it means that the system couldn't find GCC. But since you get a fatal error, no input files, it means it's all good. GCC is available. All you have to do is just follow the slides with me. Okay, so I want you to write a small program right now. So this is the code. It's a very simple one. It simply prints 2 lines on a screen. And the way you compile it is that, first of all, you save your file into, let's say, hello world.c. And then you compile it by using the compiler name gcc space hello world.c. So when it comes to Intel compilers, they are usually a little bit faster, but it really depends on the code. Today, we're going to work with GCC only. If you need to compile with something with Intel, you can simply recompile your code and just test run it and see if you get any speed up. Okay. Intel compiler also comes with its own technology. We're not going to talk about it today. We'll just focus on OpenMP. So often you get performance boost using Intel compiler. So it's worth trying. However, sometimes it's quite finicky and you have to be careful. GCC is also a very fast compiler, no need to worry about it. And remember that today, the codes that I'm using, I'm not compiling with optimization because I want to see the speed up before compiler actually does something to my code. Obviously, when you're compiling, always remember to turn on the optimization. So once you're ready to launch the job on the supercomputer, make sure you run, you compile your code with optimization. It's either -02 or 03. Okay, so we usually teach this class, of course, in front of the audience, and that's the time when I give about 10 minutes people to, just type the code and make sure it runs. But we're limited to our time, so I just continue going. And please type your questions. If something doesn't work, we will help you. So one more thing, copying from the PDF might bring you some weird characters and the code will not compile. So please make sure there are not some hidden characters that appear in your text editor. The best thing is probably just retype it if you want to follow along with the lecture. Okay, so how do you make this serial code parallel? Well, that's actually quite simple. First, we need to include the header, the OpenMP header, and you just do it by simply typing include omp.h. That's all it takes. Then you need to add a construct, a pragma command, pragma omp parallel, and then in curly braces, you type the code that you would like to run in parallel. That's all it takes. So I slightly modified the code. I created this parallel region. And inside of my parallel region, I changed the int ID from 0 to this function omp get thread num. This is the function that comes with OpenMP. And what it does is gets the name of each thread. So when you create multiple threads, multiple workers, you would like to somehow count them. You can name them, or you can simply give them an ID. And by default, that's what OMP does. It gives an ID from 0 all the way up to n-1, whereas n is a number of threads that the computer allocated for you. And in this situation, in this code, int ID will hold the ID of the thread that is running this particular code. In order to compile this little code, you need to type gcc space -f openmp space and then your file name, hello world.c. So that should give you an executable. And if you run it, by default, the output is a.out if you don't specify a file name. I'm just simply using a.out here. If you run it, you will get an output like this. So first of all, guys, if you don't have slides, they're available on our website. So how do you run it? So after running the command gcc -openmp, fopenmp, and the source code, you will get a file in your directory called a.out. This is an executable file. In order to run it, you need to type /a.out. What does it mean? That's how you run a command. You have to say that the file you're running is in a current directory. That's what // is about. Okay. If you just type a.out, Linux or your system is considering that as a as a widely known command, and it will look in a specific path. Your computer has particular directories where it's going to look for anything you type in your command line. A.out is located in your current directory, and your current directory is not in this known to the system directories. Okay, so you have to specify that I'm running my executable from the current directory. That's why you have to have // in front of your a.out. Yes, of course, you can specify using -o flag, so -o, and then you specify the executable name. It's totally fine. It's just to save typing, I just keep rewriting a.out because I can always just recompile it back. So the code is only in PDF because I have many examples here. They're quite short. I'm not asking you to retype them, of course, but after the class, if you want to play with it, feel free to just retype it. Most of my codes feel on the slide, just basically barely any lines. So again, you can try copying and pasting it, but make sure that there are no hidden characters, because the compiler will complain about it. Another thing to note is that if you run your a.out multiple times, every time you potentially would see a different output. The order of your hello world would be different. And that has something to do with the nature of how OpenMP is working. We already know that some processors are maybe more, will get a priority over other processes. So it means that in this situation, the thread number 2 actually finished faster than thread number 1. That's why it gets the right to print on a screen. Always remember that we might have multiple threads, but we only have one screen. So threads are fighting for the right to access this resource and print something on the screen. And whoever gets there first, well, gets the right to print something. That's why you have this order that's not what you expect to be 0, 1, 2, 3. No, you get in fact 2, 1, 0, 3 in this situation. And if you run the code, sometimes you might even have half of the word hello, like for example, hell, and then you will have LD for the world, because they're fighting, and sometimes you might get only partial output. So you can't remove a.out. Are you okay? So you probably are using debug job, and if you're using a debug job, you can only write and write on Scratch. So make sure you are on Scratch system, file system, and if you're on home, you can only read from there. Okay, so if you're using debug job, just make sure you're on Scratch and do everything on Scratch. After the class is finished, make sure you copy the code back on home so it's saved, because we purge Scratch quite often, once in 2 months or something like that. So the question about how many threads you get is a tricky one. We're going to talk about it more, but don't rely on that. So by default, you will get number of threads that are relative to number of cores. However, you have to be aware that different computers behave differently. Like I have Intel computer with hybrid threading enabled. So that's why when I run my code, I indeed get actually 4 threads, not 2, although I have 2 cores. So if hybrid threading is activated, is enabled, you will get double the amount of threads. But again, you're not guaranteed to do that, because if you have a machine and you requested, for example, 1 million threads, and the system just cannot give you 1 million threads, it will give you what it can. So you can request as many as you want, and we will talk about requesting number of threads, but you're not guaranteed to get them. So you always have to make sure you're checking how many threads you actually got. This is a picture I took from Wikipedia, so you can just click on the link and read more about it. That's what basically is happening with OpenMP code. It's called a fork join model. And initially, when you run your code, it runs serially. It means you have one thread. You always have it. It's called a master thread. It has an ID of 0, and you always have it. Okay, just remember, master thread is always there. After that, if you type, for example, pragma OMP parallel, you create a parallel region where multiple threads are spawned. In this situation, for example, 3 threads were created, and they all run the same code in parallel. After the code is finished, the parallel region is finished, you are down back to 1 thread, a master thread that continues, until the next parallel region is encountered. The number of threads could be different there, maybe 4 threads, maybe 2 threads. Again, the work is done in parallel, then the parallel region is finished, and you're down to 1 master thread. So that's a fork join model in a graphical representation. Now, how do you ask for a particular number of threads? Well, there are many ways of doing that. And one is to ask in your code for a particular number of threads using the function OMP set num threads. So then you specify, let's say, 8 threads, and that will work for all parallel regions after that. So all parallel regions that you create after that will be asking for 8 threads. Again, you're not guaranteed to get 8 threads, but most likely you will get 8 threads. Remember that if you need to ask for another number of threads, you have to call this command again with a different number, of course. Now, in the parallel region here, I'm using the command that we already seen. It's OMP get thread num to get the ID of the thread. And I also use a new command, OMP get num threads. And that's the command that will actually return the number of threads that were allocated. So you can ask for 8 threads, but if you got only 7, OMP get num threads will give you the 7 as a value. And that's why I store it in the variable n threads, and that's what I'm going to work with. Okay. So now if I don't have if statement after that, I will see 8 times print on a screen. There are, let's say, 8 threads. I don't really need to see that 8 times because it's the same value from every thread, the same output. So I specify that only thread with ID 0 is allowed to print. Why is it important? Simply because master thread with ID 0 always exists. So even if I run with 1 thread, it will still work. The code will still work even if I don't have any parallelization. So another way to request a number of thread is through a global environmental variable. So you're running your codes in Bash most likely or any other shell. You are able to set the variables, environmental variables. And OMP num threads is that variable that OMP will listen to. It will look for this variable, and whatever value is there, it will allocate that number of threads. So notice that my code does not explicitly ask for any number of threads. So if I'm just running this code on my computer, by default, I'll get 4 threads. If I move the same code onto Niagara, it will give me 40 threads, most likely. But if I say that I'd like 8 threads by setting the variable OMP num threads value to 8, so the first command here is a bash command, export OMP num threads equals to 8. Running this command gives me 8 threads. In order to compile, you always have to add fopenmp and make sure you included the header. So include omp.h. If you wouldn't do one or another, you'll either get an error or you wouldn't get any performance. The interesting thing is that if you're not using the specific OMP commands, OpenMP commands like OMP get thread nums, your code will actually compile fine. So you can simply comment out the pragma OMP parallel and your code will still work. That's a beauty of it. But here we're using commands that require us to include the omp.h in header. So threads and processors, are you talking about procs like as a CPU processes? So if you talk about processes as on the system, there are some similarities, but processors. Okay, so the processor is a hardware tool. Okay, it's a chip, and you can ask for many threads. So you can run with 10 threads on one processor. So they're not the same. So threads are software created. So it's done using coding. And processors are actually the hardware devices on your computer. So, okay. So this way of requesting the multiple threads are usually preferable because what is happening is that, let's say you compile the software, let's say Niagara, and you want to test it with different number of threads. Well, you do not have to recompile your code every time. You can just set OMP num threads, let's say, to 2, run it with 2 threads, and see whether you like the result or not. Then you can switch it to maybe 8 and see if you get any performance boost. With the previous example, when you have to manually change the number of threads in your code, it requires recompiling every time. So depending on your code, both approaches could be beneficial, of course. There's also a third way of doing that, and this is a local way of requesting the number of threads per parallel region. So pragma OMP parallel, and then I have another clause, num_threads, and then I say 8. So it means that this particular parallel region will get 8 threads. You can see as an example, I set my OMP num threads variable, bash variable, to 16. However, the local number of threads takes precedent over the global amount requested. So these are 3 ways that you can request different number of threads. So yes, thread equals to 0 is always referring to master thread. So basically, if you have a parallel code with multiple threads and you need to do some printing, do it just through master thread, because it's always there. If I do if thread equals to, let's say, 10, what if I only have 8 threads? So obviously it will cause an error. So thread number 0 always exists. Use it for printing, or in case you may be running your code serially. Okay, so so here we usually give our students some time to play with the code. I give a task, a serial code, and ask students to parallelize it using just the knowledge that we just got. And this is actually enough to create a parallel code. It's a quite ugly way of doing that, but people get a gist of what it means to parallelize your code. We're in a different format right now, so this kind of assignment I will give you at the end of the session. But what people usually see by writing this code is that they encounter what's called false sharing. And that has happened to do with the cache line I mentioned earlier. So here's a simple example. I have an array, 100 elements, for example, and I create a parallel region, and I'm going to update values in this array, but I'm going to update only several values. And each thread is going to update its own value. They're not going to interfere with one another. So I have parallel region, and I put in a variable I the thread number, thread ID. So OMP get thread num will return values, IDs of a particular thread. And then in a for loop, I will repeat many, many times a simple update, just increment by 1. So let's look. I have a stride variable, and let's say it's 16. So if I have a master thread currently working on updates, I equals to 0. So it will be 0 times 16, which is 0. It means that the first element of the array would be updated. Then the thread number 1 would update the element number 16. The thread number 2 will update the element number 32. Then 64, 128, and so on. So simply it's 16 times the ID of the thread. Is that clear? No questions yet? It's a very simple code. It's just to show you a particular problem that arises in this situation. So this stride variable, I'm going to vary. I'm going to change it and see how it affects my performance. So I compiled this code the same way, GCC F OpenMP, no optimization. And I ran it with the stride equals to 1. So I changed the variable value from 16 to 1, and I recompiled the code. And you can use a time command. It's a Linux command that's available to you, probably on any system. The output might be different if you're using, other than bash, a different shell, but nevertheless, you still get the time of the execution. We only look at real, the first line. It's basically how many seconds code took to run. And with the stride equals to 1, it took 22, almost 23 seconds. If I take the same code and I change my stride to 16 instead of 1, and I recompile it, suddenly the time it takes to finish is only 6 seconds. There's a huge gap between 23 seconds and 6 seconds. So how do you explain that? Well, that's what's called fault sharing. That's a tricky concept you have to be aware of. So when the processor updates a value, let's say updates a value in an array, it takes a part of this array and it stores it in its cache. Now, after the value is updated, it's updated through the cache. So in the cache line, the value is updated. And the processor thinks that the next value would be updated, maybe the neighboring one or maybe the same one. But in our situation, that's what happens in our situation. We updating two values that are close to each other, which means that this array has to be put in a cache line of the first and the second processor. But because the updates are happening simultaneously on both processors, you might have inconsistencies between the values, because if the same array is being updated on two different processors, the values will diverge because the processor doesn't know whether you need the value at the index 2 or not. So here's just an illustration of what's happening. The processor number 1 updates the first value, and then since the second processor also needs to update the second value, which is very close to the first one, they both take the same chunk of the array and they store it in their cache lines. So the cache line has a particular size. It's relatively small, but not very small. So it allows several elements of the array to be stored in it. But what happens is that because the first element is being updated by the first processor, the array has to be synchronized between these processors through the memory. So basically, every time the value is being updated, the array has to be synchronized with the memory and then uploaded into a cache line of a second processor in order to make sure that the values are consistent. And after the second processor updates its second value, in order to make sure that, again, values are consistent, the synchronization through the memory occurs again. So this part of the array is keeps bouncing between the cache lines of the first and the second processor. That significantly slows down the performance. What happens is that when the stride is 16, the cache line is only that big. It fits the part of the array that is updated by the first processor, and the second part, since they're so far apart, the element number 0 and 16, that the second part goes to the second cache line. They do not interfere with each other, if it makes sense. So basically, you would like to separate the updates and not share between the same cache lines. So it might be different to comprehend right now. I know it's a new concept. It took me a while also. But what you need to basically take away from here is that when you create an array and every thread works with every element of the array. And then you have very fast updates. For example, every nanosecond you're updating an element. Every thread is updating its own element. You're creating a lot of bouncing around between these aforementioned cache lines. So you have to make sure that the elements are far enough in the array. So let's say you're updating the first element, 16th, the 32nd, and so on. They're far enough to fit in the cache line. So then they're all processors are working independently without needing to synchronize it through the memory. Because processors know that if the value is changed in the proximity of these cache lines, that they have to be updated through the memory to make sure that everything is consistent. I guess it's enough of that. Just remember that your code might be actually slower than the serial code. Yes, that's pretty much the answer, especially if people use this approach to, for example, use an array where every thread is writing to its own element, and then they create, let's say, 4-element array, and they're writing in element 1, 2, 3, 4. You are facing false sharing. So in this situation, you would need to create maybe an array of like 100 elements and write into elements that are far apart from each other. But in fact, it's not the best approach anyway. We will learn better tools to do that. But as a first approach, it's a good thing to keep in mind. Now, I mentioned earlier that the threads, you get the most performance if everything is working in parallel. So threads do not need information from each other. But sometimes you can't avoid that. And maybe some thread needs an information from other threads before it can proceed with the calculation. A common example could be, for example, if you perform some differential equations and you parallelized it, but you need to exchange the boundary condition between the domains. So you have to do the synchronization part, meaning that you have to synchronize the threads. And there are several ways of doing that. We're going to talk about each of them with example. So critical section is a section where only one thread at a time is allowed to enter in this region. So here is an example. I have a sum that I want to calculate. So first I initialize it with 0. I create my parallel region. Now every thread is going to repeat the code in this parallel region. If I have 4 threads, I will get 4 duplications of the same code. But how do I identify it? Of course, I have OMP get thread num. It means that every thread gets its own ID. So I already have different part for every thread. And then let's say I have to perform some work based on this ID, on this thread number, thread ID. And for some reason, I need to make sure that there is no race condition. And we will talk about race condition more in depth, meaning that threads are not interfering with each other. They're maybe writing to a same database or to the same file. It has to be done serially. So you cannot allow all threads write or read from the same location at the same time. So this could be resolved by using a critical section where only one thread is allowed to perform the work at a time in this section. So it means every thread will enter the the critical section, but only one at a time. Remember, any synchronization you introduce in your code slows down the performance, simply because now threads have to wait for one another to finish. And if you have uneven, for example, load on the threads, so meaning that one thread finishes significantly earlier than the other, they have to wait for each other. So it slows down your performance. Every time you include synchronization, you're losing in performance. So if you find a way to avoid it, please do so. Another synchronization construct is called atomic, and it's kind of similar to critical, but it allows only a small update. So simply, if you have a variable and you would like to update a value, maybe you would like to just increment it by 1, or maybe you would like to multiply it by something. That's what atomic allows you to do. Atomic is faster than critical, but critical section allows you to put as many commands there as you want. So you can have a large code inside of your critical section, but atomic only allows you one atomic command, meaning update, read, write, and so on. That's it. Well, read, write, and update. That's it. That's the difference between them. The third synchronization construct is the barrier, meaning that once thread sees or pragma OMP barrier, it stops. It waits for all her friends to finish. So all threads are waiting for each other at the barrier. Once everybody got there, they proceed again in parallel from there. So that's a good way to ensure that you don't proceed until all threads finish the calculating, because maybe you need to interchange some information between the threads. Like, for example, here's a small code. My calc function needs ID and the var at the same time, so I have to wait till the all threads finish with calculating. Another construct that you need to be aware of is when you need to perform work only once. Remember how we only printed on the screen once the message? I said we don't need to see something 8 times. I wanted to see it once. Well, that's an example. I need only one thread to do that. And in order to single out one thread to do a particular task, we can use a single work sharing construct. So inside of your parallel region, you have some function that run in parallel, do work. Then you have pragma OMP single, meaning whatever thread gets here first runs the command exchange boundaries. The rest, they skip exchange boundaries and they wait for this particular thread to finish exchanging boundaries, and then they proceeding together. So it means that there is a barrier, it's called implicit barrier, at the end of the single clause. So only one thread exchanges boundaries. The rest are just waiting for it to finish. And then they're all together, continue doing more work. So another work sharing construct is very similar to the single construct, but it only allows master thread, the thread with ID 0, to perform the workload. So here I do work in parallel. Then I have pragma OMP master, which singles out the master thread. It will wait till master thread finishes whatever it's doing. And then it exchanges the boundaries. But other threads are not waiting for the master thread. They continue moving on, and they will actually do more work. But let's say I don't want to do that. I want to wait for them to finish. So I put an explicit barrier. I say pragma OMP barrier. Wait for your other friends before you continue. So that's the difference between master and single construct. By the way, there is a so-called no wait clause. It's in our slide here. I think, let me move the chat. Yeah, so if you don't wanna to wait for other threads to finish, sorry, for the single thread to finish, you can remove it by using no wait clause at the end. So it will be pragma OMP single no wait. Then it means all the threads will proceed except one that will perform the workload inside of this clause. Okay, so probably by far the most used way to parallelize your code is through for loops. So you have a for loop, and if your for loop iterations are kind of independent from one another, it's very simple to parallelize your code. So here, I, for example, have a for loop that simply prints something on the screen. and then just pragma OMP parallel 4 makes it magically parallel. If I show you the output, you can see that the workload was split between the threads more or less evenly. So thread 0, for example, took the counter I equals to 0, 1, 2. Thread number 1 got I equals to 3, 4, 5, and so on. So the workload was split between the threads. As you can see, it didn't require us really doing a lot. If you have a for loop and you know that the operations inside of the for loop are independent, it means you're not writing in the same variable. You can just put pragma OMP parallel 4 in front of it, and you get fully parallelized for loop. A very convenient way of doing that. But sometimes you might want to perform some other instructions in parallel before or after your for loop. Then you can simply, inside of your parallel region, you can type pragma OMP 4 in front of your for loop, and you achieve the same result as before, for example. So pragma OMP 4 parallel 4 is a shortcut for what you pretty much see here, except I'm also requesting a different number of threads, for example. But if you just want to parallelize for loop, you don't have to specify curly braces. You can just type pragma OMP 4 parallel 4, and that's it. So again, curly braces, I hope everybody understood. Define the parallel region. So open braces basically specifies the beginning of it, and curly braces stops the parallel region. Everything after that is single threaded. Okay, so it's also monitoring the chat. So here you can see how the workload is spread between the threads based on how many threads you're actually requesting. So you don't really have to think of it that much, but if for some reason it's important for you to know which thread is doing what, remember print is again your friend. You just can print on the screen what thread is doing exactly what workload. Now, sometimes you have parallel, you have 4 loops that are nested. So here's an example of a nested parallel loop. Oh, sorry, nested for loop. And in order to make it parallel, I simply add a collapse clause. So pragma OMP parallel 4 collapse, and then I specify how many nested loops I have. Well, in this situation, I have 2. And on the next slide, you can see how the workload was divided between the threads. How the constructor. So the curly braces specify the beginning and the end of the parallel region. So if so when you have pragma OMP parallel and then open curly braces, everything inside the curly braces until it meets the closing curly braces will be run in parallel. Everything after the closing curly braces is done in serially in one thread until the next thread, until the next parallel region is encountered. Okay. So that's a good point. Now, I'm not always having curly braces. So if I only want to parallelize the next command right after pragma, you do not need curly braces. So notice that you should be familiar with that. But if you have a for loop, and the for loop consists only of one command, you do not need to specify curly braces. So notice here I have 4, then I have 4, then I have printf. I don't have any curly braces anywhere. I can put curly braces here. I don't know if you can see my cursor, but right after my for loop, and then at the end before return, and it will be the same thing. But because my for loop consists of only one command, which is another for loop, I do not need my curly braces. Exactly, single commands do not need it. So I think it's good practice to just if you're learning, just keep using curly braces. I'm a little bit limited with the number of lines I have on my screen because I want to give you the full code so you can just copy paste it. So I'm kind of skipping on them, but if you feel uncomfortable, just keep using them until you feel comfortable and you stop using them. Okay, so there is no harm in using Pragma OMP parallel and just always open curly braces, open and closes at the end. But that's a good point I didn't mention. Thank you. So one of the, I guess, beneficial clauses is the reduction clause. That's a very helpful one. And when we work with our students, it's usually, there is some music playing, probably Zoom doing something. When you calculate a sum of something, when you have, for example, a series or just you accumulating something in a variable, multiple threads writing the same variable produce a race condition, meaning that you have to somehow separate the workload. So only one thread can change a value, or for example, writing into array. So I see people really happy when they figure out that there is a reduction clause that makes calculating sums very, very simple. So let's say here I have a code where you need to calculate some sum, well, like a summation. And I'm simply accumulating in the variable calc. How do I do that? Well, Pragma OMP parallel for parallelize the for loop. And then I have reduction clause that specifies that I would like to only let one thread at a time update my calc values. And update is atomic. You remember we had atomic update and only small update like plus or minus is allowed. Well, here I'm specifying that the plus is the operation that's going to be allowed, and the variable that's going to accumulate it is the variable calc. So basically what it means, underneath it creates a code that is a for loop, and then it will have an atomic clause here where only one thread at a time is allowed to update the calc. There is also a lot of things happening underneath. The code is produced that you're not aware of. You don't have to worry about it anyway. So what you need to remember is that if you need to accumulate something in parallel in one variable, maybe you would like to calculate a product, or you subtract something, use a reduction clause, you will get a significant speed up of their performance. And as you can see, it's just one line. So it's very, very simple. So here is an example of the output. So serial code on my right runs for in 12.5 seconds. And the same code with this just one line added runs in 5.5 seconds. There is significant speed up. Notice that you don't get a linear speed up. I have a four threads available, but I don't get speed up of 4 times. But I get a significant improvement simply because allocating threads still takes some time. So you never really get this linear performance saying that if I run it for 12 seconds, now with 4 threads, it will be running in 3 seconds. Not really. The time is still taken to create threads, to discard them, and so on. So, but you get a quite decent performance boost. Now, there are multiple commands, multiple operators available for the reduction clause. You also need, of course, an initial value. There are several commands available again. The OpenMP form standard has a lot of functionality in it. We are barely scratching the surface today, just to get you started if you need to parallelize your code. And if you familiarize yourself with OpenMP, like especially the latest standard, which is a version 5, it actually has a custom reduction clause. It means that you can use reduction with any operator, and in fact, even a class that you have in your program. So it doesn't have to be plus or just minus, but it's usually enough to perform simple mathematical operations. So if you need to perform a reduction on a complex operator, it's possible, but you have to read the manual. So another thing I want to briefly talk about is scheduling. So we have our for loop, and by default, the workload is divided between the elements, between the threads, kind of evenly, more or less. So basically, every thread gets a chunk of this for loop to work on, and there is no shuffling happening in between. So basically, it's allocated based on, of course, how many iterations I have and how many threads in total I have. The workload is split between them, and threads are just carrying on until they're done. Sometimes that's not what you want, and there are also a couple of other scheduling available. You have dynamic, you have also guided auto, and so on. I'm only mentioning here static and dynamic because that's what I find most probably used, but just be aware there are other types of scheduling as well. So let's just look at the example. I have a simple code for loop, and on each iteration, I'm simply sleeping for 0 seconds, sleeping for 1 second, for 2, 3, and so on, up to 19 seconds. So the last iteration will sleep for 19 seconds. I'm simply simulating the workload that is uneven. It means that one iteration takes significantly longer than the other. Sometimes could be a case. Sometimes your iterations finish almost at the same time. So depending on case on a case how your workload is spread, you would choose one schedule over another. So here I'm using schedule static, and I'm specifying one. By default, schedule is static, but the number of threads, a number of elements in a chunk is based on the number of iterations and the number of threads. So not one. I'm specifying directly here that I want one iteration per chunk. And I'm also specifying, for example, 10 threads. After compiling it, that's the result I get. So with the default chunk size, you can see that the total amount of time it was 37 seconds. And if you think, why is it like that? One thread got iterations 18 and 19 together. And if you add 18 and 19, you get exactly 37 seconds. So one thread was working on the longest 2 iterations. So there's a way to improve that. How do you do that? Very simple. If you do chunk size of 1, it means that the threads will start taking what's available once they finish. So there's a pool of work, and let's say one thread, the thread, for example, number 0, once it's finished, it will get the next workload, for example, counter number 5, and so on. So there's a predetermined schedule who works on what, but they work on it one step at a time. So here you can see that, of course, one thread worked on iteration 19, but the total time is only 28 seconds. It means that another thread, the one that took the longest, so not thread number 9, was also working probably at the number 9. So because 9 and 19 will give you 28. Clearly you have an advantage here. I only use 10 threads. So if I have, for example, Niagara with 40 cores, obviously the total time would be equal to the slowest iteration, because each thread is doing everything independently. There is no delay, so it will be 19 seconds. So dynamic is a little bit different from static. By default, it will be like static with a chunk size of 1. However, with the static, the order is predetermined. So basically, the threads already know which loop counter they're going to work with. In dynamic, that simply there is a pool, and whoever finishes first takes the next workload from this pool. And it might be helpful, but be aware that dynamic gives a little bit more overhead than static, but sometimes it might be negligible to give the performance boost that you want. So here is an example. Default chunk size for dynamic is actually 1. So you get, again, 28 seconds max. And if I change the chunk size, it means that each thread is going to work on 2 counters in the loop. So clearly one thread got 18 and 19 iterations together. That brought us to 37 seconds running time in total. So another thing I want to briefly mention is data sharing. And everything that you define before you start your parallel region, so before your Pragma OMP parallel, is considered shared. It means that every thread can see the values defined before the parallel region. It's called the variables are defined on a heap, and they're available again for every thread. So here is an example. I have X defined before the parallel region, and then I'm incrementing in my parallel region X. I actually get some more or less accurate result, but it doesn't have to be that way, because you have to remember that every thread is going to try to increment. And if they're stepping on each other's toes, you can simply get some values that are different every time you're running your program. Even right now, printing on a screen is not in the same order, because I also have print statement. Means that the second thread got to it faster than the first one. So again, this is an example of shared data. And when you change in your parallel region shared data without taking care of it properly, this will give you race conditions. So please be aware of that. You will get different results all the time. So if you compile the code and you keep rerunning just the same code over and over again, you will get different results. That's a clear sign of race condition. Now, everything defined inside a parallel region is considered private. It's created on the stack, and it means that only the thread can see this information. It's not shared between the threads. So threads do not see private data of each other. So I have variable here X, that's 10, defined outside of the parallel region. It's shared. But then I define X inside, and I assign a value of 5. This X is private to every thread. So it means when I'm running the code, it says that every thread has X equals to 5, but shared hasn't been touched. It's still 10. So private variables are really safe to use, and it's probably a good idea to run your calculations using private variables. Writing into shared variables is dangerous. Reading, though, is okay, because when you're reading, you're not changing anything. But writing, you have to be very careful with. So let's say you have a shared variable and you'd like to somehow make it private. There are several ways of doing that. And this is just like an overview of available clauses. And I'm going to just give an example on each of them. So let's say I have a variable X, that's 10. It's shared, means every thread sees it. I want to make it private. So Pragma OMP parallel private X basically tells compiler to take X and define it inside of the parallel region. Please be aware that this clause does not initialize the variable with any value whatsoever, which means that if the value, the variable is defined in the memory and there's some garbage in it, you will see some weird values. You cannot rely on it. So you have to initialize it with a particular value. So here I'm initializing it with X equals to 1. Means now inside of my parallel region, X is 1. Outside it's still 10. Now it might be helpful if you're going to initialize your values, your private values inside private variables inside of the parallel region. But what if you just want to have a copy of your shared variable and you want to work with it? Well, first private is what you need. So pragma OMP parallel first private X, and it simply makes a copy of the shared variable, and it's safe to use, update, whatever you want to do inside of the parallel region. Outside, it's still X equals to 10, nothing changed. So first private is a safe way of working with data. Another thing is last private. Haven't really used a lot of it, but basically it's taking a shared variable, it makes it private, and then you make some updates. The last update is carried out of the parallel region. So if X was 10 before and 3 was, let's say, the last update of the variable, outside X also is 3. I wouldn't suggest using that very often unless you really have a case for it. So now probably the pinnacle of our lecture is the default clause. So default clause is a magical clause that ruins your code. It literally breaks your code completely. So I have a simple code here, pragma OMP parallel. I have some array, I have some values, and I'm printing on something on the screen. The moment I type default none and I recompile my code, I get a bunch of errors. So what's good about it? Well, default none means that the variables are not shared by default anymore. It means that you have to manually specify whether the variable is private or shared. And this is very helpful because if you have a code in the parallel region that's a couple of lines, that's probably easy to trace which variables you have there. But if you have 10, 20 lines of a quite complex code, you might forget that certain variables are shared and others are not. So I would suggest you break it by using default none and then fix it by specifying whether the variable should be carried as private or stay as shared. So if you're updating something, make sure that you may be using some synchronization construct for that as well. So you have to take care of it very carefully. OpenMP is very powerful. It's sometimes a one line to make a code parallel, but with this kind of power, you have to be careful of what are you putting there. So as you can see here, after I specify that X is private and my array is shared, I recompile my code and everything is good. That's pretty much all that I have for today. Now I want to give you some assignment. So this is the assignment we usually give our students during the lecture, so people can get accustomed to using OpenMP. And usually it's given in progression, meaning that first people suffer and try to parallelize the code using like arrays and all this assumption that they have just based on knowledge that you have an idea of the thread. Then they learn about synchronization construct, and then they're trying to use synchronization proper constructs to help them. Then they learn about reduction, data sharing. Eventually, they're experts. It's one-liner that helps solving their code. So I will ask you to kind of probably skip the painful aspect of it and just try to implement the parallelization using the reduction and data sharing. Of course, if you want to play with your code, try to use synchronization. Try to just use as minimum as possible, just maybe an ID over the thread. Try using an array, see if it slows down your performance. So I'm giving you the answer. This is the serial code that solves the problem above. It's a simple for loop, basically, that you need to just accumulate values into a sum variable. So there's nothing really difficult in this code. If you feel there is something you don't understand, just send us an email or ask a question on the forum. So you just need to basically add one line that will make this code parallel. You have to watch for the data racing conditions. So it means that if you run your code multiple times, you still get the same value of pi. The result should be pi. And I ask you also to use a time command to compare the performance between serial and parallel version of your codes. So you definitely should get a speed up, quite decent one, but maybe not like 40 times if you're running on Niagara. If you go on our website, the educational website, the part with assignment, there is an assignment description there. I also gave an example what it took to run it on my computer. Give it a try. See how it runs on your computer, what kind of speed up you get. And make sure to submit it to our assignment Dropbox. You just have to leave the file there. There is no submit button. So we just see the latest version you updated. So do you guys have any other questions? Well, in any event, tomorrow we have a kind of an office hour session where anyone can just join us and ask questions. So you have something to work on, see what kind of errors you encounter. We'll try to help you. We usually, of course, help people with the computers. We just literally sit with them and we help, because sometimes people forget like semicolon at the end, right? And that's normal. That happens. We're learning, right? But we see that right away. People sometimes don't see that. We might be able to share the screen next time to be able to help you. But nevertheless, try to formulate your questions so we can help you kind of remotely. But it's definitely a different format for us right now. Anyway, on Thursday, I'm going to present you with my solution to it. And we'll see how you guys performed as well. So what is that? Do you guys hear the music? I don't know if it's Zoom doing something. Hopefully it didn't bother you very much. So I think that's all for today. If you have any questions, just please continue asking us. And I thank you for your participation today. And hopefully we see each other tomorrow. Thank you.